In this video, we're going to talk about convection heat transfer, but first let's review conduction heat transfer. Remember, conduction heat transfer uh, typically would occur when you have like heat transfer through some solid. Let's say it's T1 on this side, T2 on this side, and your heat transfer is going to be Ka over T1 minus T2 over the length L, where length is the length of this. Now, in this case here, we're assuming that these edges are well insulated. So we have some length and there's some surface area in the front and back. Surface area A, K is a thermal conductivity. So this was conduction, heat transfer. And then convection occurs, maybe most typically, let's say you have some kind of a maybe surface here, and it's at some temperature, maybe call it, say, T1, and then you have maybe air flows over the surface, let's say like this, and it's flowing at a certain velocity, and the air or gas or liquid, it could be any of those things, it has some temperature TF. And so again, this is for convection, that the heat transfer rate is going to be HA T1 minus TF, like this. So once again, we're assuming the heat is transferring up this way. Now, I should mention a couple things in these cases I'm showing here. Of course, heat is always going to transfer from the hotter side to the cooler side. So, like in this case up here, we're assuming it's going to be T1 is greater than T2. Otherwise, we'd have to show the arrow going the other way. And the same with convection showing here, we're assuming that this temperature of the surface down here, which you're calling T1, is greater than the temperature of the fluid. And so heat is transferring up this way. Again, we can have forced convection or free convection. Forced convection, again, will be the case when maybe some air is being blown over the surface or some liquid is running over the surface. And then free convection is just when it naturally flows uh, out, even when there's no air above it. So, excuse me, even when there's no flowing air or flowing liquid. Well, let's say it's stagnant, but because of buoyancy, there's going to be heat transfer. Now, this is very similar again to our conduction heat transfer equation. The only difference is instead of having a thermal conductivity, we call this H the heat transfer coefficient. That's our H. And these can often be found in tables or they'll have to be given to you. And also remember when we talked about conduction, we said that this equation could be rewritten like this. And we could think of this being like some kind of resistance to the heat transfer. So we would call that maybe are, let's say in the case of conduction, I know you can call it COND maybe, like this, where this is going to be that denominator, like this. And it'll often be handy to think of it in terms of resistance like this. There will be times, though, it'll be more convenient to use the equation directly. But again, many times it'll be easier to use this equation here and consider this resistance. So in the same way we have for convection, we have where we said HA, let's say T1 minus TF, for example. And again, this can be rewritten like this. This is going to be written like this. So once again, we can think of this fraction here as being some kind of resistance. We'll call it R convection. So we could use this equation here to calculate our convection heat transfer. Like this. Take a look at this example. Cold air flows over glass with a heat transfer coefficient of 30 BTU per hour feet squared degrees Rankine. The temperature of the air is 2 degrees Fahrenheit, and the temperature of the glass is 20 degrees Fahrenheit. Yes, this actually should be 20 degrees Fahrenheit. And what is the heat transfer rate Q? Now, we're not given the surface area, so we're going to have to calculate this per cubic foot of surface area. So what we'll do when we have our normal equations, again, our equation is going to be HA, and I'll just, since we only have two temperatures, I'm just going to call it T minus TF. Again, TF is the temperature of the gas or the fluid, in this case, the air. And I'm going to rearrange this a little bit. Again, since we don't know the area, we'll calculate this per square foot like this. So divide both sides by A, and that'll give us HAT, excuse me, HT minus TF like this. And then if we substitute our values in, now since this is going to be a difference, we can keep it in Fahrenheit because the difference between two temperatures in Fahrenheit is going to be the same as the difference between two temperatures in Rankine. So we'll keep it in Fahrenheit. And so our heat transfer coefficient is 30. Again, our T of the glass is 20 degrees Fahrenheit minus 2 degrees Fahrenheit. Again, since it's a difference, the difference in Fahrenheit, same as the difference in Rankine, so I'm just going to call that R. And so we'll calculate this. And so the heat transfer rate is going to be 540 BTUs per hour foot squared. Again, if we knew the surface area, we could multiply this value by the surface area, and then we would have BTUs per hour. But it's often the case you won't be given the surface area, and often the case that you just want to find it. Basically, in this case, the heat transfer per 1 square foot. Next, we're going to look at combined conduction and convection. We've looked at conduction, looked at convection, but sometimes we may have a case where we have, say, something like this. We have maybe some kind of medium here, and your heat transfers through this by conduction, but then also we may have convection, maybe out here, and maybe convection out here. And so let me call this a TF1 and maybe call this a T1 and a T2 and maybe call this out here TF2. And so you can sort of think of, once again, sometimes you can handle these as resistances. Sometimes that's useful. Um, or sometimes it's more useful just to do these separately. But let me just make some resistors here. So let's say here, this could be thought of as your TF1, T1, T2, TF2. Again, then this is convection. Here, we said the resistance for convection is 1 over HA. And for conduction, it's L over KA. And then for this convection here will be 1 over HA. Now, in some cases, we may be calculating things, the flow rate per unit area. So in which case, these could end up being like 1 over H, 1 over, excuse me, L over K, or 1 over H if you're doing them per unit area. And now, the most important thing to remember, though, when you're calculating these, again, you could calculate either Q dot if you know the area, or you can calculate Q dot over, say, per square foot or per square meter, something like that. But always remember the heat transfer rate has to be the same all the way through. So often the strategy is to calculate the heat transfer rate for in the area that you know enough unknowns that you can calculate. So for example, again, the heat transfer rate, let's say if you're doing it per unit area, is going to be the same all the way through. And let's say maybe this TF1 and this T1, and the heat transfer rate, then you can calculate this heat transfer very easily right here. And then once you get that heat transfer rate, you can kind of work to the next value. You can use conduction here, convection here to find the other temperatures. So what I mean, like, let's say if we find, let's say, per unit area up here, this can be H, again, assume we're going this way. This is going to imply that this is bigger than this. So that's going to be TF1 minus T1. Then in this region here, this would be K over L uh, T1 minus T2. And finally, in this region here, Q over A dot is H. Then this time it's going to be T2 minus TF2, like this. So if you know, again, like I said before, if you know enough to calculate the heat transfer here, or maybe you know enough to calculate the heat transfer here, this one, or you know enough to calculate the transfer here, heat transfer here, these Q dot over A's will all be the same, and the Q's will all be the same. So you can calculate one, you can use that to calculate other information you need. So for example, maybe as I said, maybe you have these two temperatures, and of course you have to know this heat transfer coefficient. Then you can calculate the Q dot over A and use that in this equation to find this T2. Then when you find that, you can use this equation to find TF2. So that's a common strategy for solving problems like this. Let's take a look at this problem. We have air flowing over glass, similar to the last problem. And again, the air is minus 5 degrees Fahrenheit, a little bit lower than the last problem. The glass temperature on the outside is 20 degrees Fahrenheit. Then the glass is zero point 0.3 inches thick. And we want to find T1, which is the temperature on the other side of the glass, and F1, which is the temperature like of the air on the other side of the glass. So let's take a look at this. Often the way to approach these problems is to start by calculating a place where you know uh, you can find some information. So keep in mind a couple of things. Q dot, or if it's a Q dot per area, is the same through all the layers. In other words, the heat transfer from here to the glass, through the glass to the other side, and from glass to the air, it's going to be the same. So if we can find the heat transfer rate for any of those steps, then we're going to be able to solve this problem. Now, kind of keep in mind, let's sort of we're probably not going to have to use resistance too much in this, but just kind of get an idea of the picture that we have. So like this would be, say, going from our TF1 to our T1, and then going through the glass. I'll call that T2 at our 20 degrees. And then on out to our TF2, which is at minus 5 degrees. So that's just a picture. We may not need to use resistances, but you can think of it this way. Now, there are probably some ways you could solve this to use it. What I'm going to do is I'm going to work with this up here. I'm going to find the heat transfer at the end. In other words, I'm going to calculate, uh, and you can maybe call it from this section right here from T, from 2 to say F2, and that's going to be HA. Again, we're not given the area, we're not given the surface area, so we're gonna have to calculate like this per square foot. So I'll divide both sides by area A, and that's gonna be H T2 minus T F2. And again, we know the heat transfer coefficient out here, 35 BTUs per hour foot squared degree Fahrenheit. And again, at T2 was 20 again, because we're dealing with a different, doesn't matter if we had Fahrenheit or Rankine, and minus a minus 5 Fahrenheit like this. And that's going to be 35 times 25, which is 875. And the Fahrenheit going to cancel. BTUs per hour foot squared like this. And now remember that heat transfer rate is going to be the same all the way through. So now we can use this to find T1. We're going to work backwards. Next, we're going to look at the heat transfer through the glass. And again, that's going to be conduction. The T1, because I call it our 20 degrees at T2. And of course, we always want to have the warmer temperature here and the lower temperature here. Now, so again, we want to solve for T1. Again, just looking at our picture here. So that's what we're solving for. So let's actually rearrange this to solve for T1. And then when we rearrange this, these will go on the positive side. Let me actually put those then on the right. Again, we're solving for T1. So we'll divide through by K over L. When we do that, that'll cancel. And then we'll have a reciprocal here. That'd be L over A. Excuse me, L over K, like this, plus T2 like this. Now we can substitute our values. Again, remembering that the heat transfer rate has to be the same all the way through. And we calculated the heat transfer for this last portion to be 875. So we're going to put that in to here. And then our length was 0.3 inches, but everything else in feet. So we're going to have to multiply that by 1/12. That'll give us feet. And our K value would be the K value for glass. Now in my book, it's in chart B3. And if we look down B3 under glass, uh, it's zero point 0.8. It's zero point 0.8 BTU per hour foot Rankine. And that's going to be plus our T2. Now our T2 was our 20 degrees. I'm going to change that to Rankine just so everything is correct. Again, because we're working with differences, we don't have to do that. But just to be sure, let's go ahead and do that. Now, again, let's just check how our units are working out here. Over here, the BTUs are going to cancel. We have a foot here. It's going to go in the numerator. So that'll give us foot squared. Foot squareds are going to cancel. And the hours are going to cancel. And then we have a 1 over r in denominator. That's going to go to the numerator. That'll give us another Rankine. So everything's looking good. We'll have a Rankine here and a Rankine here. And when we do that, this quantity here comes about 27.3. And we add that to our 480. That's 507.3 Rankine, like this. Or it's going to be about 47 degrees Fahrenheit, like this. Now, finally, we want to find the heat transfer from the glass to the inside air. That's going to be by convection. And again, that would be this TF1 T1. And again, we want to find out what this TF1 is. So let's solve. I'm going to distribute that. That'll give us H times each of those. Then I'm going to bring the HT1 on the other side, but then reverse the equal sign. I'll show you what I mean here. And again, when we divide through by H, oh, excuse me, when I brought the other side, this should have been a positive right there. Because I multiplied by this and brought it to that side. And then, but we divided by the H, so that'll go away. And so if we do that once again, we know what our heat transfer rate is. We got that at the beginning of the problem, 875. And this H, the heat transfer coefficient on the inside is 14. Again, I'm going to write it as degree R. Again, it doesn't matter if we're dealing with differences. And then finally, plus our T1, which we just found a minute ago, 507.3, like this. Yeah, let's just check our units here. Beat to user cancel, foot squared or cancel, hours or cancel. Then we have 1 over R, which brings an R up in the numerator. And this here, TF1 is 62.5 R plus 507.3 R. That gives us this. And then TF1 is 109.8 degrees Fahrenheit.